Transformation of functions. We all know that a flat mirror enables us to see an accurate image of ourselves and whatever is behind us. When we tilt the mirror, the images we see may shift horizontally or vertically, but what happens when we bend a flexible mirror? Like a carnival funhouse mirror, it presents us with a distorted image of ourselves, stretched or compressed horizontally or vertically. In a similar way, we can distort or transform mathematical functions to better adapt them to describing objects or processes in the real world. In this section, we will take a look at several kinds of transformations. Graphing functions using vertical and horizontal shifts. Often when given a problem, we try to model the scenario using mathematics in the form of words, tables, graphs, and equations. One method we can employ is to adapt the basic graphs of the toolkit functions to build new models for a given scenario. There are systematic ways to alter functions to construct appropriate models for the problems we are trying to solve. Identifying vertical shifts. So one simple kind of transformation involves shifting the entire graph of a function up, down, right, or left. The simplest shift is a vertical shift, moving the graph up or down, because this transformation involves adding a positive or negative constant to the function. In other words, we add the same constant to the output value of the function regardless of the input. For a function g of x equals f of x plus k, the function f of x is shifted vertically k units. See figure 2 for an example. To help you visualize the concept of a vertical shift, consider that y equals f of x. Therefore, f of x plus k is equivalent to y plus k. Every unit of y is replaced by y plus k, so the y value increases or decreases depending on the value of k. The result is a shift upward or downward. Vertical shift. Given a function f of x, a new function g of x equals f of x plus k, where k is a constant, is a vertical shift of the function f of x. All the output values change by k units. If k is positive, the graph will shift up. If k is negative, the graph will shift down. How to? Given a tabular function, create a new row to represent a vertical shift. 1. Identify the output row or column. 2. Determine the magnitude of the shift. And 3. Add the shift to the value in each output cell. Add a positive value for up or a negative value for down. Identifying horizontal shifts. We just saw that vertical shift is a change to the output or outside of the function. We will now look at how changes to input on the inside of the function change its graph and meaning. A shift to the input results in a movement of the graph of the function left or right in what is known as a horizontal shift, shown in figure 5. For example, if f of x equals x squared, then g of x equals x minus 2 squared is a new function. Each input is reduced by 2 prior to squaring the function. The result is that the graph is shifted 2 units to the right because we would need to increase the prior input by 2 units to yield the same output value as given in f. Horizontal shift. Given a function f, a new function g of x equals f of x minus h, where h is a constant, is a horizontal shift of the function f. If h is positive, the graph will shift right. If h is negative, the graph will shift left. How to? Given a tabular function, create a new row to represent a horizontal shift. 1. Identify the input row or column. 2. Determine the magnitude of the shift. And 3. Add the shift to the value in each input cell. Combining vertical and horizontal shifts. Now that we have 2 transformations, we can combine them. Vertical shifts are outside changes that affect the output y-axis values and shift the function up or down. Horizontal shifts are inside changes that affect the input x-axis values and shift the function left or right. Combining the 2 types of shifts will cause the graph of a function to shift up or down and right or left. How to? Given a function in both a vertical and a horizontal shift, sketch the graph. 1. Identify the vertical and horizontal shifts from the formula. 2. The vertical shift results from a constant added to the output. Move the graph up for a positive constant and down for a negative constant. 3. The horizontal shift results from a constant added to the input. Move the graph left for a positive constant and right for a negative constant. And 4. Apply the shifts to the graph in either order. Graphing functions using reflections about the axes. Another transformation that can be applied to a function is a reflection over the x or y axis. A vertical reflection reflects a graph vertically across the x-axis, while a horizontal reflection reflects a graph horizontally across the y-axis. The reflections are shown in Figure 12. Notice that the vertical reflection produces a new graph that is a mirror image of the base or original graph about the x-axis. The horizontal reflection produces a new graph that is a mirror image of the base or original graph about the y-axis. Reflections. Given a function f of x, a new function g of x equals negative f of x is a vertical reflection of the function f of x, sometimes called a reflection about or over or through the x-axis. Given a function f of x, a new function g of x equals f of negative x is a horizontal reflection of the function f of x, sometimes called a reflection about the y-axis. How to? Given a function, reflect the graph both vertically and horizontally. 1. Multiply all outputs by -1 for a vertical reflection. The new graph is a reflection of the original graph about the x-axis. 2. Multiply all inputs by -1 for a horizontal reflection. The new graph is a reflection of the original graph about the y-axis. Determine even and odd functions. Some functions exhibit symmetry so that reflections result in the original graph. For example, horizontally reflecting the toolkit functions f of x equals x squared or f of x equals absolute value of x will result in the original graph. We say that these types of graphs are symmetric about the y-axis. A function whose graph is symmetric about the y-axis is called an even function. If the graph of f of x equals x cubed or f of x equals 1 over x were reflected over both axes, the result would be the original graph as shown in Figure 17. We say that these graphs are symmetric about the origin. A function with a graph that is symmetric about the origin is called an odd function. Note, a function can be neither even nor odd if it does not exhibit either symmetry. For example, f of x equals 2 raised to the x power is neither even nor odd. Also, the only function that is both even and odd is the constant function f of x equals 0. Even and odd functions. A function is called an even function if for every input x, f of x equals f of negative x. The graph of an even function is symmetric about the y-axis. A function is called an odd function if for every input x, f of x equals negative f of negative x. The graph of an odd function is symmetric about the origin. How to? Given the formula for a function, determine if the function is even, odd, or neither. 1. Determine whether the function satisfies f of x equals f of negative x. If it does, it is even. 2. Determine whether the function satisfies f of x equals negative f of negative x. If it does, it is odd. 3. If the function does not satisfy either rule, it is neither even nor odd. Graphing functions using stretches and compressions. Adding a constant to the inputs or outputs of a function changed the position of a graph with respect to the axes, but it did not affect the shape of a graph. We now explore the effects of multiplying the inputs or outputs by some quantity. We can transform the inside input values of a function, or we can transform the outside output values of a function. Each change has a specific effect that can be seen graphically. Vertical stretches and compressions. When we multiply a function by a positive constant, we get a function whose graph is stretched or compressed. vertically in relation to the graph of the original function. If the constant is greater than 1, we get a vertical stretch. If the constant is between 0 and 1, we get a vertical compression. Figure 19 shows a function multiplied by constant factors 2 and 0.5, and the resulting vertical stretch and compression. Vertical stretches and compressions. Given a function f of x, a new function g of x equals a f of x, where a is a constant, is a vertical stretch or vertical compression of the function f of x. If a is greater than 1, then the graph will be stretched. If 0 is less than a and a is less than 1, then the graph will be compressed. If a is less than 0, then there will be a combination of a vertical stretch or compression with a vertical reflection. How to. Given a function, graph its vertical stretch. 1. Identify the value of a. 2. Multiply all range values by a. And 3. If a is greater than 1, the graph is stretched by a factor of a. If 0 is less than a and a is less than 1, the graph is compressed by a factor of a. If a is less than 0, the graph is either stretched or compressed and also reflected about the x-axis. How to. Given a tabular function and assuming that the transformation is a vertical stretch or compression, create a table for a vertical compression. 1. Determine the value of a. 2. Multiply all of the output values by a. Horizontal stretches and compressions. Now we consider changes to the inside of a function. When we multiply a function's input by a positive constant, we get a function whose graph is stretched or compressed horizontally in relation to the graph of the original function. If the constant is between 0 and 1, we get a horizontal stretch. If the constant is greater than 1, we get a horizontal compression of the function. Given a function y equals f of x, the form y equals f of b of x results in a horizontal stretch or compression. Consider the function y equals x squared. Observe figure 23. The graph of y equals 0.5x of squared is a horizontal stretch of the graph of the function y equals x squared by a factor of 2. The graph of y equals 2x squared is a horizontal compression of the graph of the function y equals x squared by a factor of 2. Horizontal stretches and compressions. Given a function f of x, a new function g of x equals f of b of x, where b is a constant, is a horizontal stretch or horizontal compression of the function f of x. If b is greater than 1, then the graph will be compressed by 1 over b. If 0 is less than b and b is less than 1, then the graph will be stretched by 1 over b. And if b is less than 0, then there will be a combination of a horizontal stretch or a compression with a horizontal reflection. How to. Given a description of a function, sketch a horizontal compression or stretch. 1. Write a formula to represent the function. 2. Set g of x equals f of b of x, where b is greater than 1 for a compression or 0 is less than b and b is less than 1 for a stretch. Performing a sequence of transformations. When combining transformations, it is very important to consider the order of the transformations. For example, vertically shifting by 3 and then vertically stretching by 2 does not create the same graph as vertically stretching by 2 and then vertically shifting by 3. Because when we shift first, both the original function and the shift get stretched, while only the original function gets stretched when we stretch first. When we see an expression such as 2f of x plus 3, which transformation should we start with? The answer here follows nicely from the order of operations. Given the output value f of x, we first multiply by 2, causing the vertical stretch, and then add 3, causing the vertical shift. In other words, multiplication before addition. Horizontal transformations are a little trickier to think about. When we write g of x equals f of 2 of x plus 3, for example, we have to think about how the inputs to the function g relate to the inputs to the function f. Suppose we know f of 7 equals 12. What input to g would produce that output? In other words, what value of x will allow g of x equals f of 2 of x plus 3 equals 12? We would need 2x plus 3 equals 7. To solve for x, we would first subtract 3, resulting in a horizontal shift, and then divide by 2, causing a horizontal compression. This format ends up being very difficult to work with because it is usually much easier to horizontally stretch a graph before shifting. We can work around this by factoring inside the function. F of b of x plus p equals f of b multiplied by x plus p over b. Let's work through an example. F of x equals 2x plus 4 squared. We can factor out a 2. F of x equals 2 multiplied by x plus 2 squared. Now we can more clearly observe a horizontal shift to the left 2 units and a horizontal compression. Factoring in this way allows us to horizontally stretch first and then shift horizontally. Combining transformations. When combining vertical transformations written in the form AF of x plus k, first vertically stretch by A and then vertically shift by k. When combining horizontal transformations written in the form f of bx plus h, first horizontally shift by h and then horizontally stretch by 1 over b. When combining horizontal transformations written in the form f of b multiplied by x plus h, first horizontally stretch by 1 over b, and then horizontally shift by h. Horizontal and vertical transformations are independent. It does not matter whether horizontal or vertical transformations are performed first. Access this online resource for additional instruction and practice with transformation of functions. Function transformation, openstackscollege.org.